Imagine taking a blurry, pixelated photo and magically sharpening it into a crystal clear masterpiece. Today, we're uncovering a breakthrough AI technique that does exactly that, without losing its memory along the way. Welcome to our podcast, Artificial Intelligence, papers and concepts curated by Dr. Satya Malik and narrated using AI-generated voices.
Thank you. It's really great to be jumping into this one.
Yeah, absolutely. So we are going on a deep dive today into a highly technical but honestly remarkably elegant paper from researchers at the National Cheng Kung University.
Right, and it focuses on something called single image super resolution, or SISR for short.
Which, just simply put, is looking at how a machine can take a low-resolution image and, hallucinate those missing details with startling accuracy.
Exactly. And the researchers here introduced a new architecture called DRCT. That stands for Dense Residual Connected Transformer.
But what makes this deep dive worthwhile for you listening isn't just that they built a new model. It's that they actually mathematically exposed this fatal hidden flaw in the deepest layers of our most advanced imaging AI.
Yeah, and then they built a structural patch to fix it. It's a phenomenal piece of forensic architecture, honestly.
It's a forensic architecture. I like that.
Well, because for the last few years, the AI community just operated under this assumption that vision transformers had basically solved the spatial awareness problem.
Right.
But this paper demonstrates that our state-of-the-art models were quietly starving themselves of high-frequency data right at the most critical stage of the whole reconstruction.
Which is wild.
Okay.
So let's lay the groundwork before we get to that hidden flaw. To appreciate the patch, we really need to understand the pipeline that AI uses.
Right, the history of it.
Yeah. For a long time, convolutional neural networks, CNNs, they were the heavy lifters in this space.
They were, yeah. But the paper calls out CNNs for suffering from what we call an inductive bias.
And when we see that term thrown around in computer vision, it's usually just a polite way of saying the model makes some pretty stubborn assumptions.
That is a great way to put it. The primary assumption being that pixels that are physically close to each other are inherently more related than pixels far apart.
Okay, so it prioritizes local neighborhoods.
Right. That is the core of a CNN's inductive bias. Because of how they're built, CNNs process an image through convolution kernels. You can think of them as essentially small filters sliding over the image.
Right, sliding window style.
Yeah. And their receptive field, which is the total area of the image they can analyze at any given moment, is heavily parameter dependent. You are limited by the size of those kernels and the depth of the layers.
It kind of reminds me of looking at a massive complex painting through a paper towel tube.
Oh, that's a perfect analogy.
Yeah, like you could perfectly see the tiny details directly in front of you, like a singular brushstroke or maybe a speck of blue paint, but the broader context is completely missing.
Exactly. You miss the shadow in the top left corner that, dictates how the light should hit the subject's face in the bottom right.
Yeah.
You are really just getting local details.
Before we move on to how transformers solve that, I do need to quickly say, this podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
So getting back to that paper towel tube analogy, you basically miss the long-range dependencies, which are vital.
Because if you're trying to reconstruct a high-resolution 4K image from a compressed thumbnail, you need non-local information.
Right. A texture pattern on a brick wall on the far left side of an image might be the exact blueprint the AI needs to fill in a blurry patch on the right side.
Wow, okay.
And because CNNs really struggled to bridge that gap without becoming, computationally massive, the field shifted toward vision transformers.
Right, specifically leaning on the SWIN transformer architecture, right? Now, transformers are famous for powering large language models like ChatGPT because they process the entire context of a sentence at once.
Yeah, they use global attention.
But applying global attention to an image is notoriously difficult. If a transformer calculates the relationship between every single pixel in a high-res image, the computational complexity just explodes.
Oh, absolutely. It would melt the GPU.
Right. So how did the SWIN transformer adapt that global attention for vision?
Well, the SWIN architecture introduced something called a shifting window attention mechanism.
Shifting window. Okay.
Yeah, so to avoid calculating global attention across millions of pixels simultaneously, the model divides the image into distinct local windows.
Kind of like a grid.
Exactly, a grid. And it calculates the attention only within those specific boundaries. This keeps the computational complexity linear rather than quadratic.
Wait, wouldn't that just make it act like a CNN again? Just trapped in its own little boxes?
It would, except the subsequent layer shifts those window boundaries by half a step.
Ah, so it overlaps the borders from the previous layer.
Precisely. That overlap creates a bridge for the information to cross. It allows cross-window communication.
Got it. So information can flow globally across the entire image over successive layers.
Yeah, and models like SwinRR adopted this and became the gold standard. They could finally model global spatial information efficiently.
So on paper, we threw away the paper towel tube. The AI can see the whole canvas. It can share info across the grid. We should be getting perfect reconstructions.
We should be.
But that is exactly where the researchers at National Cheng Kung University noticed something strange happening under the hood.
Right. They decided to visualize the internal states of these top-tier transformer models like SwinIR and HAT across various benchmark data sets.
And what were they looking for exactly?
Specifically, they mapped out the feature map intensity. You can think of this as like a thermal camera for the network's attention.
Okay, a thermal camera.
Yeah, it shows exactly how much spatial information the model is actively holding on to at each individual layer.
And I'm assuming that intensity should remain consistently high or even grow as the network gets deeper and prepares to output the final, highly detailed image.
That is the logical assumption, yes. But the visualization revealed a really severe, abrupt oscillation.
What do you mean by oscillation?
Well, the intensity is robust in the shallow, early layers of the network, but as the data propagates deeper, as it approaches that final reconstruction phase, the feature map intensity suddenly collapses into a very small, narrow range.
Wait, it just collapses. The network is basically just dropping the data.
It is bleeding spatial information, yes.
Wow.
The researchers formalized this by applying what's called the information bottleneck principle. Mathematically, it's expressed as a strict inequality.
Okay, play the math on me.
So the mutual information between the original input, let's call it X, and itself is greater than or equal to the mutual information between an intermediate layer Y and the input X.
Okay, making sense so far.
Which is, in turn, greater than or equal to the mutual information between a deeper layer Z and the input X.
Right, meaning that as data passes through consecutive layers, the mutual information strictly decreases. It's an absolute mathematical boundary.
Exactly. So by the time the network reaches the very end, it has essentially forgotten the high-frequency architectural blueprints it extracted way back at step one.
Hold on, though. I have to push back on that. That doesn't make sense.
How so?
Well, the whole selling point of a vision transformer and that fancy shifting window mechanism you mentioned is to see the big picture and retain long-range dependencies. Why would it suddenly develop amnesia right at the finish line?
It's because of the way deep networks pass data forward to avoid vanishing gradients. They rely heavily on something called residual connections.
Okay.
In a standard residual block, instead of pushing the heavy, full image data through every single computational layer, you teach the network to only learn the differences.
The residuals.
Right, the residuals between the input and the output of that specific block.
Which, I mean, that's standard practice. It makes training a 100-layer deep network vastly easier and way more stable.
It does stabilize the gradient flow locally, but while it works beautifully in small neighborhood blocks, the paper proves it does not guarantee the stable transmission of full spatial information across the entire macro architecture.
Ah, so it's a leaky pipeline.
A very leaky pipeline. As the data reaches the deepest layers, the network is literally starved. It's trying to render crisp edges and fine textures, but the high-frequency spatial details have degraded too much to be useful.
So we have this leaky pipeline destroying our 4K images. If standard residual connections are causing the leak, do we just throw them out entirely? Or is there a way to plug the holes?
Well, you certainly don't throw them out, or the network wouldn't train at all. Instead, the researchers redesigned the pipeline's core unit.
Okay, this is the DRCT part.
Yes, they created the SDRCB, that is the Swin-dense residual connected block. They took the shifting window attention of the transformer, but they injected dense connections directly inside the residual groups.
Dense connections. So, honestly, this sounds like a relay race where instead of a runner passing the baton to the next person and just stopping, every single runner who has held the baton just keeps running alongside the new guy.
I love that visual, yes.
Right, because by the time you reach the finish line, the entire team is crossing together, ensuring the baton, which is the high-frequency spatial information, never gets dropped.
That feature reuse is the absolute key here. In standard networks, A layer only sees the output of the layer immediately preceding it.
Just the guy passing the baton.
Right. But with these dense connections, deeper layers can reach back and directly pull multi-level spatial information from the shallower layers. The previous feature maps are simply concatenated with the current ones.
I see. So it provides a kind of global auxiliary supervision. You aren't just trusting layer 49 to remember what layer 2 saw. Layer 49 can just look directly at layer 2's nodes.
Exactly. And the paper proves mathematically that this stabilizes the forward propagation process.
Did they run that thermal camera visualization again on the new model?
They did. When they ran the feature map intensity visualization on their new DRCT model, that sudden, alarming crash at the end of the network was completely eradicated.
Wow, so no more dropping the baton.
None. The feature maps gradually and stably enhanced throughout the entire network depth, without those severe oscillations.
So the receptive field stays massive, and those high-frequency features survive all the way to the reconstruction phase. It completely bypasses that information bottleneck.
It really does. It's brilliant.
But, architecture is just theory until it actually renders an image. I want to look at how DRCT actually performed against the datasets the industry relies on, like SET5, Mango 109, and Urban 100.
Well, the empirical results are very robust. DRCT achieved state-of-the-art performance across all those benchmarks.
Yeah.
But honestly, the visual comparisons on the Urban 100 dataset are particularly revealing.
Because Urban 100 is basically filled with geometric nightmares for AI, right? Like repeating lines on skyscrapers, grids of windows.
Oh, it's brutal.
Yeah, those patterns usually cause terrible aliasing, where the AI gets confused and outputs this smudged, blurry mess because it loses the spatial context of the lines.
And the older model, suffering from that bottleneck we discussed, they simply didn't have the high-frequency data surviving to the end to resolve those tight, repeating grids.
But DRCT could.
DRCT restores those crisp structural lines beautifully. And to quantify why it's capable of doing this, the researchers measured the model's diffusion index.
Let me see. I'm looking at this diffusion index, or DI metric, in the notes. And it seems to be measuring the spread of the pixels the model is paying attention to during reconstruction.
That is an accurate way to look at it, yeah. The DI is an attribution-based analysis metric. It essentially quantifies the range of pixels that actively contribute to the final rendering of a specific patch.
So a higher DI means the model is activating a much wider field of attention.
Correct. And DRCT scored a significantly higher DI than the competing HAT model. It empirically proves that the dense connections successfully maintain a larger receptive field. The network is literally using more of the image to make its final decisions.
That makes total sense. But there's usually a catch with these benchmark-crushing models. I mean, usually when a team achieves state-of-the-art, it's frequently because they just threw a massive, bloated, power-hungry model at the problem.
That is often true, yeah.
But I'm looking at the parameter counts here, and DRCT runs on 14.13 million parameters. The previous top model, HAT, requires 20.77 million. How is the new model leaner while doing more?
It all comes back to the efficiency of that feature reuse.
The relay race.
The relay race, exactly. Because the dense connections allow deeper layers to directly access the raw feature maps of earlier layers, the network doesn't have to waste computational power or FLOPs redundantly calculating and carrying that baseline information through every single step.
Oh, well. So it lowers the FLOP count while paradoxically increasing the available information at the end of the pipeline.
Yes. So the efficiency curve is completely different. Drastically different, actually. The paper plots a performance versus model complexity chart.
And how does it look?
Well, models like SWEN-IR and HAT were plateauing. Scaling them up by adding millions of extra parameters was just yielding diminishing returns. They were hitting a structural wall.
Because of the bottleneck.
Right. But because DRCT solves that underlying bottleneck flaw, its performance curve continues to climb steeply with less compute.
That is exactly the elegant engineering we're always looking for. It's not just brute force, it's a fundamentally smarter pipeline.
Absolutely.
But architecture is only half the battle. You still have to train the thing.
Yeah.
I saw they use this three-stage, same-task progressive training strategy.
Yes, quite a mouthful.
Yeah, which starts with pre-training on ImageNet just to initialize the parameters, but then they split the fine-tuning into two distinct loss functions. They use L1 loss first, followed by L2 loss. Why split it up like that?
It is a very deliberate choice based on how those mathematical loss functions penalize errors. So, L1 loss calculates the mean absolute error. It is very robust to outliers, meaning it won't drastically alter the network's weights for a single weird pixel.
Okay, so it's fantastic for teaching the model the broad structural strokes of image reconstruction.
Exactly. But L2 loss calculates the mean squared error.
Right. And because it squares the difference between the prediction and the reality, a small error isn't a big deal, but a large error gets penalized heavily.
Which makes L2 perfectly suited for the final stage. Once the L1 phase has built the general structure, the L2 phase aggressively targets and punishes large outliers, like glaring singular pixel artifacts or minor color bleed. It basically acts as a final high-grit polish on the image.
And that rigorous combination of a dense connected architecture and a progressive training strategy clearly paid off. The paper notes they took this model into the entire 2024 Image Super Resolution Challenge.
Which is a huge deal in the community.
Right. It's one of the most competitive global proving grounds for vision AI, and they secured top-tier results in both the validation and testing phases.
It is just a remarkable validation of their hypothesis. They didn't just build a good model, they identified a fundamental limitation in deep feature extraction and engineered a mathematically sound bypass.
It really changes how you think about the images you see every day. I mean, the next time you watch a blurry, compressed video suddenly snap into crystal clear 4K resolution on your screen, you'll know exactly the kind of microscopic relay race happening under the hood to make sure the AI doesn't drop the baton.
Yeah, and it leaves us with an incredibly compelling, broader question to consider, honestly.
What's that?
Well, if an invisible information bottleneck was secretly holding back our top-tier imaging AI right under our noses, what other advanced deep learning fields might be suffering from the same thing?
Like what?
Like natural language processing or autonomous medical diagnostics, they might be silently suffering from their own forgotten data bottlenecks, just waiting for a structural patch like dense connections to unleash their true capabilities.
Man, that is a phenomenal thought to leave on. Thank you to everyone listening for joining us on this deep dive. If you want to keep exploring the hidden mechanics and structural breakthroughs defining the future of artificial intelligence, make sure you subscribe to the show. Until next time.